Welcome back to Science Click. Today, is it possible to go faster than light? We often hear that the expansion of the universe accelerates some objects faster than light itself. Indeed, some objects see the distance that separates them increase faster than the speed of light. But this is due to the expansion of the universe itself, the underlying grid upon which are placed all entities. This grid is in constant expansion, which is why the distance between objects constantly grows larger. This is not actually true movement. It does not enable us to send information faster than light. Except for the expansion of the universe, is it possible for an object to move faster than light through space? The theory of special relativity enables us to grasp the fact that the speed at which an object moves in space modifies the flow of that object's time. The faster the object moves relative to the observer, the more the object's own time slows down in comparison to that same observer's time. If this same moving object carried a clock, then the time taken for the arms of that clock to go full circle would be greater than the time taken by those of an identical clock which would lie at rest in the object's environment. So the quicker an object moves in space, the slower it moves in time. To quantify this situation, we can try to draw a very simple graph which represents the passing of time in relation to the speed of an object. For an object at rest, with a speed of 0, time passes at 100% of its normal rate. In turn, for an object travelling at 100% of the speed of light, time would simply stop, or in other words, go by with a speed of 0. Naturally, we might think that if time can come to a stop when we reach the speed of light, it might be possible to take it one step further and go back in time if it were possible to travel even faster than the speed of light. The more we would accelerate beyond the speed of light, the quicker we would be going backwards into the past, with a flow of time that would be negative. This is an idea which seems at first glance entirely plausible and even very attractive. However, it relies on a fundamental assumption which should not be left unchallenged. This is the fact that we have extended and connected both points by a straight line. Indeed, there exists a certain curve which connects these 2 points and upon which are placed all objects of the universe. Any form of matter, any object, can be found on this curve, and as soon as it begins to move at a certain speed, time relative to that object will inevitably flow at a determined pace. In short, time comes to slow down in the same way for all objects, given that they have the same speed. When we look to see whether or not this curve is actually a straight line, we find out that an object moving at 50% the speed of light sees its own time go by not at 50% of normal rate, but at 87% of the normal rate of the flow of time. Likewise, an object moving at 80% the speed of light sees its own time go by at 60% normal rate. And an object moving at 25% the speed of light sees almost no difference as its own time goes by at 97% normal rate. The curve which appears before our eyes turns out to be not a straight line, but a quarter circle. And any matter contained in the universe can be placed somewhere along this quarter circle. Just like our straight line, this curve can be extended until forming a full circle. Left of the graph, the negative speeds simply correspond to speeds attained while moving in the opposite direction. If moving towards the right gives a positive speed of 1 mile per hour, for example, then moving with a negative speed of -1 mile per hour simply equates to moving towards the left with that same speed. To start things off, we see that it is neither possible to go faster than the speed of light, nor to go beyond the rate of 100% the flow of the observer's time. Indeed, even for a hypothetical object which would be going back in time, that is, with a flow of time that would be negative, it remains strictly impossible to go beyond the speed of light, because all objects are confined to this circle. The question then is not to know if it is possible to go beyond the speed of light, but rather to understand why such a thing is impossible. Why our curve takes the shape of a circle, and what is so special about the speed of light. Let us begin by looking at the particular shape of this curve, a circle. One of the key properties of a circle is that all the points which compose it are situated at an equal distance to its centre. For any object, the only meaningful measure is neither the speed at which it moves, nor the rate at which its own time flows, but rather the distance from the centre of the graph. This measure takes into account both the object's movement in space and its movement in time. It is in sorts a unification of the two speeds. We combine both the object's movement in space and in time. This is speed in space-time. Whatever the speed of an object, whether it speeds up or slows down, its position in the graph will change, but its distance to the centre will always stay the same. This measure is a fundamental constant, universal. It rules over all entities in the universe. It is this same measure we call the speed of light. It is important to understand that the speed of light is something fundamental. Its importance does not come from the fact that it is the speed at which light travels. Its importance comes from the fact that in space-time, when we consider both space and time, it is the speed at which all objects in the universe move. With this in mind, we can get a better understanding of the phenomenon at hand. Objects cannot go beyond the speed of light because they actually move with that precise speed under all circumstances. The only thing which can change is the way in which an object's speed is distributed over space and time. If the object is rather high up in the graph, it gives a lot of its speed to time and very little to space. Its own time flows with a rate that is very close to normal, but it moves very slowly in space. This is the sort of behaviour exhibited by objects in our everyday lives, which are either at rest compared to us, or moving very slowly in comparison to the speed of light. On the other hand, if the object is more towards the bottom right-hand corner of the graph, it gives more of its speed to space than time. The fastest objects in the universe move very fast in space, and consequently, very slowly in time. They actually evolve in time in slow motion compared to us. This is the case for light in particular, which gives all of its speed to space, leaving none to time. A light particle moves extremely fast, but its own time does not pass at all. If a light particle carried a hypothetical clock with it, the arms of that clock would not even move. An object which speeds up does not actually gain speed. It will only convert its temporal speed, the one which enables it to move through time, into spatial speed, which enables it to move through space. This is equally true the other way around. An object slowing down is one which converts a part of its spatial speed into temporal speed. It slows down in space and consequently speeds up in time. On the whole though, its speed in space-time has remained constant. It is still moving at the speed of light. It is only the distribution of that speed over space and time which has changed. To conclude, this representation in the form of a graph has many advantages, as it is very visually appealing and enables us to intuit certain phenomena. For example, we might wonder whether or not there exist objects in the lower part of the graph. Intuitively, such objects would be going back in time, since their temporal speed is negative. Following this reasoning, we might be able to postulate that there exists a specific kind of particle in the universe which would be situated in this part of the diagram. This type of particle is what is commonly called antimatter. Antimatter particles have identical properties to regular particles, only their electric charge is reversed. They are in essence the symmetrical counterpart of ordinary particles. The part at the top of the graph is where regular matter is, while in the bottom part, its mirror image is the world of antimatter. As for light particles, also known as photons, these are themselves their own symmetrical counterparts, being on the horizontal axis. They are their own antiparticles. It is important to remain cautious, however, since all this representation is only based on the model of special relativity, which holds only in an empty and perfectly flat universe. In reality, our universe is not flat, it is filled with stars and planets, which distort in 4 dimensions the geometry of space-time. Under these conditions, we must look to the theory of general relativity. In general relativity, gravity does not exist. It is the curvature of space-time which naturally converts an object's temporal speed into a spatial one. If an apple, which was originally at rest, falls from a tree, this is because its evolution in time was gradually converted into an evolution in space, in other words, a speed, as a result of the curvature of space-time which is due to the Earth. If we observe from far out an object situated next to a massive entity like the Earth, then the graph associated with that object will begin to distort itself. Next to a black hole, the circle becomes so distorted that it becomes smaller and smaller as the object comes closer to the horizon. When the object reaches the event horizon, the circle has become entirely contracted. This means that the object has no margin left for movement. From our point of view, it stays motionless, at rest with the surface of the black hole. When we observe them from far out, all objects which fall into a black hole end up appearing stuck on its surface. But for the object itself, this phenomenon is only an illusion. From its point of view, it is possible to go through the horizon of the black hole and gradually continue falling towards the central singularity. However, for us, observing the situation from outside, all information contained by this object slows down until it reaches a final stop and remains fixed on the surface of the black hole. One of the most important consequences of this phenomena is that the entropy of a black hole, meaning in a sense its information and temperature, is entirely distributed along its surface.